You get a little shock, but not that much. So it's an amperage that will kill you, and connection of those two. Give you another example. Your car, when you start your car, you know how much voltage goes through your battery to your starter? 24,000 volts. But the amperage is less than 1 amp. That's why if you touch the spark plugs, you get a shock, but you don't get killed.
1 million.
1 million.
Million.
So, anyway, this is the HVDC converter station, and we have 2 in California, 1 in Adelanto, 1 in Selma. The Adelanto will bring power from Arizona and Utah, and the 1 in Selma will bring power from Oregon and Washington State to Southern California. These converter stations owned jointly by Southern California Edison and Los Angeles Department of Water and Power to bring power to LA Basin, not the city of LA. All right. Now, again, when we said we have a transmission, the high voltage is going to come in, it's got to go somewhere. What we call it switching station or distribution station. That's when you see these racks, we call it bus, that all those high voltage power will come to these various buses, and from there, they go to transformer, capacitors, switch gears, and so on, power relays. And it goes to the control room. The control room is a guy with about 25 monitors and sitting and looking at it and punching in his computer, switching one line to another line. This power goes this way, that power goes that way. So it's very sophisticated and complicated, system. I don't want to bore you with the details of that, but the function of this switching station is to bring the power from various transmission lines all to one point, and from there send it to various substation, from substation to be distributed to the local. Now, again, the distribution part of it is what happens. Again, we have the generation, we have the transmission. This side of it, which is in green, this is where we start distributing. And the distribution happens from a substation, it's called local substation. For instance, if you look around this campus, there is a huge substation within 1.5 miles from this campus. This substation there provides power not only to this campus, within a radius of 5 miles from that distribution system. So all the businesses, industrial facilities, if there is one, this campus, all the houses, apartments, everything's all fed from that distribution. And then distribution line is different than transmission line. Because they have a lower voltage, we can put it underground. Today, because a lot of citizens complaining about the ugly wooden, pole and on the street, and then have 2-3 lines over it. And nobody wants to see that, especially you open the window, you want to see the ocean view. Instead of that, you see ugly, things there. And it's not safe for birds, because birds sit there and if they open their wings, they can touch the other line and they can get killed. So because of that, now the new rule instead of California is any new area that you're developing, the distribution is all underground. Because it's a lower voltage, we have less to worry about the heat transfer that it's generating through the cable. Therefore, we can put it underground. And you see a lot of that on the new areas. Like, for instance, if you go see Irvine, they're going to need out. Rancho Santa Margarita. These places, you don't see those poles anymore. Still, the very overpopulated area like Long Beach, LA, we still see those because really there's not much of an option. And putting them underground, you've got to dig. Once you start digging, you see there are telephone, things that are sewer pipe, storm drain pipe, water pipe, gas pipe. There are so many things there that you really don't have any room to put a cable. So that is a part that we call distribution, that it gets on a lower voltage distributed to the end users. That is the definition of a distribution. Now, if you want to look at it, this is, of course, this part that is generation, and it's going to be transmitted, and then it comes down. These are the distribution, goes to various houses. And for that, one of the things that we're pushing in today's market, let's have this solar, let's have a small power plant and connect it to this distribution line. Rather than building a huge power plant, transmit it, go through all those stations and all those craziness, and then bring it down to this guy. We can have a little small solar project connected to that. That's what we call this side distributed generation. So we generate the power, we put it right on the distribution line and give it to the customer. There is no middleman, there is no transmission involved, there is no grid involved. Same thing here, we build the power through wind and put it in the distribution. And even smaller fossil fuel power plant, what we call cogeneration or 10 megawatt gas turbine, we can do those and get rid of all those large, huge power plant and transmission going from one state to another state, and then getting power from North Carolina or getting power from Mexico and so on and so forth. Because that system is so complicated, and most importantly is old, falling apart, and overloaded. They're beyond their capacity. In electrical engineering system, when we design any electrical system, we always make sure that whatever the line, the capacity line is, it's 1.5 times of what we need. So if we are trying to transmit a 500,000 volts somewhere, we design the system to the capacity of 750,000 volts. Today, that line has 780,000 volts on it. There is no room for adding more power to that line. And we keep needing more power every day. We can't stop using our cell phone. We can't stop using our computers. We are too sophisticated now. We cannot go backwards. We got to move forward. And as we go forward, our demands for power goes higher and higher on an hourly basis, on a daily basis. So that is the future that we're looking for. Generating power in a smaller version, especially through renewable sources, and then dump the load right into the distribution,